Hi, this is the second video for Exponential and Logs Part 2. In the last video I talked about E. So just to recap, E is just a base number, approximately 2.718, whereby if you have y equals e to the x, then its special property is that when you differentiate e to the x, you get e to the x. So its gradient function and the function are the same. So the good thing about this, the useful thing, is that if we model something where something is growing or decaying exponentially, then we can use E to model, and the calculations then become easier because we can work out the rate of growth or the rate of decay because it's easy to differentiate. When we're talking about exponential growth and decay, we're talking about something growing or decaying over time. So in terms of a graph of exponential growth and decay, the horizontal axis is always time, and it could be in seconds, it could be in minutes, it could be in years. Okay, so this horizontal axis will always be something to do with time, and because it's time, it's never going to go below 0. The vertical axis, well, that's whatever it's talking about, so it might be the population of something, it might be the number of something, it could be cost, it could be whatever it happens to be. Okay, so you'll have one variable representing the scenario, what it's about, and then you've got time. Now this is showing exponential growth. Okay, so something that's increasing as time increases, and this is showing decay. P is decreasing as time decreases. In terms of the formula, well, part of the formula is going to be e to the t, okay, but it's not going to just be that due to the fact that the numbers are going to be different, the model's going to be different, so there will be some constants. There might be a letter representing some sort of vertical stretch, and we tend to use capital letter A. There might be a letter representing some sort of horizontal stretch, and we use a lowercase k. So this is showing exponential growth. There might be a constant. This could be negative. This could be negative. If you've got a negative value here, then the shape of the graph is like that. Okay, but the main part of the formula will involve this. For it to go that way, this has got to be negative. So if you have something that's like that, generally it's going to be exponential decay unless there are other things going on. Okay, so you're going to see lots of formulae that look like this in part. Right, let's have a look at a scenario just to give you an idea of the sorts of things that they will ask you in exponential growth. So we're just going to look at a few questions just to give you an idea. We are going to look at more exponential growth and decay questions in another video where they are a bit more complex. Okay, so this one's about mice. I bought 3 mice, assuming that the growth can be modelled as m equals a e to the 0.5t, where m is the number of mice and t is the time in months. Calculate the values of a and k. Well, we've got k, so we can just ignore that. That shouldn't be there. So we just want the value of a. We also need to know the number of mice after 6 months. We also need to know the rate of growth after 6 months, and we also need to comment on the validity of the model. So lots of the questions that you do, you'll have to do all or some of these types of problems Okay, sometimes they'll give you all of this, other times they will give you information for you to work it out, and then the rest of the question is using the completed formula. Right, so it says I bought 3 mice, so we're going to say that that's when t equals 0. So at the start of the model I have 3 mice, so we can use this now to work out m. So for part A, if m equals a e to the 0.5t, then when t is 0, m is 3. When t is 0, I have 3 mice, so 3 equals a e to the 0, which means that a must be 3, because e to the 0 is 1. Okay, so our actual formula is m equals 3 e to the 0.5 t. So this now is what we are going to use for the rest of the questions. Part B. Calculate the number of mice after 6 months. So we need to know what m is when t equals 6. So m is 3 e to the 0.5 times 6. And we can just stick that into our calculator. So 3 e to the 3. The number of mice is 60.25 and so on. So therefore 60 mice. Okay, and I've just rounded it to the nearest whole because we're talking about mice. Okay, now it says the rate of growth after 6 months. So if it says anything to do with rate, we are talking about differentiation. Okay, we are going to differentiate our formula, the rate of growth after 6 months. So if you think of the graph, will look a bit like that, roughly. Here's time, here's m. We're actually after, where t equals 6, we're actually after the gradient on the curve at that point. That's the rate of growth, or the gradient of the tangent, however you want to look at it. So we're going to do, if m equals 3 e to the 0.5t, then dm, so we're differentiating m with respect to t, dm by dt, and then we just need to differentiate. Remember, it's this, e to the 0.5t will be 0.5 e to the 0.5t, but then we've got 3. So 1.5 e to the 0.5 t. And this is the gradient function, so we need to know at t equals 6, we need to know what that gradient is. So 1.5 e to the 3. Oops. Press that button. So 30.1 to 3 significant figures. Okay, so the rate of growth after 6 months is 13.1 mice. Okay, I'm just going to leave that to 3 significant figures because we're not after a number of mice, we're after a rate. So I'm going to leave that as a decimal as opposed to rounding it like I did in the previous one. Okay, so that's the rate that is growing. So at that instant where t is 6, there is an increase of 30 mice. That's what that means. Okay, and then for D, comment on the validity of the model. So quite often you'll be expected to do this, where you're looking really at the long-term model, what happens as t gets bigger. So as t gets bigger, so tends to infinity, e to the 0.5t, well, what happens to that as t gets bigger and bigger? As t gets bigger and bigger, that's just going to go bigger and bigger and bigger and bigger and bigger and bigger. So as that gets bigger, then that gets bigger. So as t gets bigger and bigger and bigger, tends to infinity, then that will also tend to infinity. So therefore, what it's saying is that the number of mice is going to tend to infinity. Is that valid? Okay, so I would probably say that that's not valid. It would be, I suppose, if mice were left alone and there was no environmental factors, but there are environmental factors. Mice get wiped out, there might be floods, there might be an influx of cats. I know my cat keeps a number of mice down because most of them end up dead in my kitchen. So we're talking about long term, how valid is it? So I would say not valid for t tending to infinity as environmental factors should be taken into account. So when you're asked something like this should be your first bit. As t tends to infinity, what's happening to the e part? What does that mean for the population? And then the rest of it, you just need your sensible hat on and think about what in real life does that mean. Okay, so that's just an example of the types of things. Okay, so let's look at 3 actual examples. They're all slightly different. Okay, question 1. The price of a used car can be represented by the formula P equals 16,000 e to the minus t over 10, where P is the price in pounds and T is the age in years. So P is the price in pounds, T is the age in years. Calculate the new price. Well, the new price is going to be where T equals 0. So for A, where T equals 0, P is going to be 16,000 e to the 0, which is £16,000. So when new, the price is 16,000. B, the value at 5 years old. So we want to know what it is when t equals 5. So 16,000 e to the minus 5 over 10. So that is £9,704 and 49p. Okay, it's not said how to round it, so I've just rounded it to the nearest p. Okay, and then C, what the model suggests about the eventual value of the car. Okay, so again, this is to do with this bit here. What is happening to this bit as t gets bigger and bigger? So as t tends to infinity, because you've got it suggests the eventual value of the car. So the eventual value of the car suggests that t is just going to keep getting bigger and bigger. The car's just going to get older and older and older and older. What's happening to that? Well, this one, in terms of a graph, will look like that. So as t is getting bigger and bigger and bigger, this is getting smaller and smaller and smaller. So this is tending to 0. Therefore, P would end up as 16,000 times 0 as t gets bigger and bigger. So the eventual value of the car is 0. Okay, which is possible. Some cars just end up on the scrap heap. Some cars become vintage. So I suppose it would depend on the car. Okay, but in terms of our model, as t tends to infinity, this bit, so it's always to do with this bit. So whenever you're asked something about the model, long term, then you start off with as t tends to infinity, then you've got your e bit, and then what happens to the other variable. Okay, question 2. The number of elephants in a herd can be represented by the equation n equals 150 minus 8e to the minus t over 40, where n is the number of elephants in the herd and t is the time in years after 2003. So t is the time in years after 2003. Okay, so this is slightly more complicated. You've got this bit on it by itself will be in decay, but then you've got transformations of that. Okay, calculate the number of elephants in the herd in 2003. So if t is the time in years after 2003, then the number of elephants herd in 2003 will be where t equals 0. So if I put t equals 0 in, 150 minus 80 e to the 0, so that's 1, so it's 150 minus 80, which is 70. So in 2003, there were 70 elephants. The number of elephants in the herd in 2007, so in 2007, that's going to be when t equals 4. So n equals 150 minus 80 e to the minus 4 over 40, or minus 1/10. So 150 minus 80 e to the minus 1/10. So that is 77.6 or 78 elephants. So you can see that the number of elephants is increasing. What is the rate at which the population is growing in 2010? So again, we're now asked for the rate of growth. So we are going to need to differentiate. So for C, we're going to do dn by dt. So derivative of 150 is nothing. The derivative of this, well, it's going to be 80 times by a 40th. So that's 2, and then it's going to be positive. So 2e to the minus t over 40. So it's minus a 40th times by minus 80. is 2e to the minus t over 40. So at t equals, so in 2010, that's going to be when t equals 7, dn by dt is going to be 2e to the minus 7 over 40. Minus 7 over 40. So that is 1.68. So at the instant where t is 7, the rate of increase, this is positive, so there is an extra 1.68 elephants at that instant. Sketch the graph of n against t. So you've got two options here. Either you need to use graph transformations, or we can maybe put some points in. We've already got 2 points, so it might be worth just doing that. So we've got t against n. We know at t equals 4, n equals 70. So at t equals 0, n equals 70. So the first value there is 70. At t equals 4, let's say there, n equals 78. Okay? Let's say when t equals 10, what's happening when t equals 10? Well, there'll be 150 minus 80 e to the minus a quarter, which is 88 nearly. Okay, so we're getting this sort of shape like that. Okay, let's see what happens when t is bigger. Let's see what happens when t is 40. T is 40, 150 minus 80 e to the minus 1 when t equals 40. That's 120.6. Okay, so you can see it's increasing like that. And then question E, predict the long-term population of the herd as predicted by the model. So again, it's to do with what happens long-term. T tends to infinity. What is happening to this bit here? Oh, I wasn't supposed to colour over it. What is happening to this bit here? Well, that bit there, as t gets bigger, this bit is tending towards 0. If this is tending towards 0, then n is going to tend towards 150 minus 80 lots of 0, which means n is tending towards 150. So as t gets bigger and bigger and bigger and bigger, n is tending towards 150. So actually in terms of the graph, there is going to be an asymptote here at 150. That's what's happening. Okay, so the long-term population of the herd, it's just going to get closer and closer and closer to 150. I guess in reality, that's not likely to happen, but it is a model and would probably be useful up to a certain point. Okay. Last one. The density of a pesticide in a given section of field is p milligrams per metre squared. Can be modelled by the equation p equals 160 e to the negative 0.006t, where t is the time in days. since the pesticide was first applied. So use the model to estimate the density of the pesticide after 15 days. So when T equals 15, P is 160, E to the minus 0.006 times 15. E to the minus 0.006 times 15 equals, so that's 146 milligrams per metre squared, so three significant figures. B, interpret the meaning of the value 160 in this model. Well, P is 160 when T is 0. So when T equals 0, P is 160. So that is going to be, in terms of the model, that's going to be the density of the pesticide in a section of field when T is 0. So when it's first applied. Okay, so that's how much pesticide is in the field when it's first applied. Okay, so it's the amount of pesticide in the field when it is first applied. Okay, show that dP divided by dt equals Kp, where K is a constant, and state the value of K. So the gradient function is in terms of P. P is in terms of T. So we're going to have to find a connection. Just change colour. P is 160, e to the negative 0.006 t. So it's saying to do something with dp by dt. So if I do dp by dt, it's going to be 160 times by negative 0.006, not the t, 0.006, e to the negative 0.006 t. So 160 times negative 0.006 is negative 0.96 e to the negative 0.006 t. Okay, but P is 160 e to the negative 0.006 t. So if there was 160 e to the negative 0.006 t, we could change that to a p. Okay, so this is just a multiplier of this. So we just need to figure out what that multiplier is. Okay, so if we do negative 0.96 divided by 160, we will get negative 0.006 times 160 e to the negative 0.006 t, which is actually there, to be honest. Don't think I needed to do all of that. But I thought it through. I can just go back to here. dp by dt. There is the p, 160e to the negative 0.006t. So it's negative 0.006. And then there's the p, which means that k then must be negative 0.006. Okay, so actually I didn't need to do any of that. Apologies, that was a waste of time. Okay, so show that dp by dt is kp. So I've differentiated it. There's the p, so that must be k, and then I've replaced that with a p again. Interpret the significance of the sign of your answer to C. Well, this is the rate of change. So because this is negative, then that means it must be decreasing. Remember, this is a gradient, so we've got a negative gradient. So that must mean that the amount of pesticide is decreasing. Is decreasing because we have a negative gradient function, a decreasing function. And then the last part, sketch the graph of P against T. So sketch the graph of P against T. And we only need the first quadrant. So there's P, there's T. When T equals 0, P is 160. So when T equals 0, P is 160. And then it's just going to go like that sort of shape. Okay, obviously not across the axis. Converge to the axis. Okay, so the numbers can be a bit awkward, but very much doing the same thing over and over and over again. Okay, so please have a little practice of those, exercise 14C, and that's the end of that video.